All right, we are now on to the last question of the AP Calculus BC exam for the year 2023, again on the non-calculated portion. And you had to see it coming. You knew you were going to get a Taylor series question, and here it is in its full glory, all three parts, and they even threw in a Lagrange error-bound question in there. So I'm pretty excited about this. Quick note before we begin, my kids are watching Harry Potter downstairs, and my 2-year-old is up from his nap. So if you hear background noise, then just pretend it doesn't exist because we are focused on Taylor series right now. All right, so here's our problem. We've got a function f, and they don't actually tell us what the function is, but we don't actually need it to write a Taylor polynomial. But we do need some information about its derivatives. It is known that f of 0 is equal to 2, so the function evaluated at 0 is 2. F prime of 0 is equal to 3. The second derivative is given just as negative f of x squared. And the third derivative is written as negative 2x times f prime of x squared. So I know this seems a little weird because we don't actually have the function itself, but it is really just testing to see, do we understand the structure of how to build a Taylor polynomial? And they're trying to get a little creative with what they're writing for our first or second and third derivative values. Excuse me, not values, but actual second and third derivatives. But we have enough here. So first off, find the fourth order derivative of f with respect to x, and then write the fourth degree Taylor polynomial once we know that for f about x is equal to 0. So show the work that leads to your answer. Okay, so let's set this up. So we got a couple things going on here. So first things first, we need to find the fourth order derivative. So we need to find the fourth order derivative. Well, in order for us to find the fourth derivative, we just need to differentiate the third derivative, right? The fourth derivative is the derivative of the third derivative. So if I want to differentiate this right away, we have to recognize we need to use the power rule, right? So the power rule, we would say again, a prime times b plus b prime times a. And you could switch that around however you want to do it. But doing that, I've got negative 2 times f prime of x squared. So I just went ahead and I differentiated this, left this alone. Now I'm going to add to it that switched around. I'm going to leave this alone and then differentiate this. Again, just basic product rule here. So we've got plus negative 2x times f double prime of x squared. But again, if we're differentiating all of this, we have to also utilize the chain rule, which we're always doing whenever we're differentiating. Oops, that should be 2x. Okay, and you could rewrite that, but if you just left that as it was, that's fine. And keep in mind what we just did is the product rule. So if you're still confused about how we got that derivative, just remember, we're just using the product rule, okay? All right, so now that we have that, we can evaluate that fourth order derivative about where the function is centered, or it says about x is equal to 0. And we're doing this because we're going to need to find the fourth order derivative evaluated at where it's centered to write its coefficient for our Taylor polynomial. So this is just going to be negative 2 times f prime of 0, okay, plus, well, all of this right away, we know that if we're evaluating this at 0, this is just going to be equal to 0, right? And what is f prime of 0? That's where, we have to use our given information. We're told that it's equal to 3, so this is negative 2 times 3, and that's equal to negative 6. So the next thing, I think we actually have pretty much everything else that we need. Oh, we also need to find the third order derivative evaluated at 0. But again, we kind of saw that from our previous step. This is going to be negative 2 times 0 times f prime of 0. Again, since we have a 0 here, this is all going to be equal to 0. Okay, so let's set up our Taylor polynomial. So our Taylor polynomial is, so our function evaluated at where it's centered at 0, so which is 2, plus the first order derivative evaluated at 0, that's also given to us, that's 3 times x to the 1 over 1 factorial. Now, normally I wouldn't write all that, but we're going to clean this up in a second anyway, so might as well. Now we're adding to it our second order derivative evaluated at 0, which I didn't actually show, but it probably should have, f double prime evaluated at 0 up here. This is going to be equal to negative 2. okay? So this is going to be minus 2x squared over 2 factorial. Okay, this again, this basic repeated structure of the Taylor polynomial, and if you need help with this, please watch my video on it. I'll try to link it in the description below. Plus, now our third order derivative, we found that that was 0, so you technically don't need to write it, but I'll just stay consistent for now because I'm going to simplify everything anyway in just a moment. Minus now what we just found by evaluating our fourth order derivative, evaluated at 0, which is negative 6 times x to the fourth over 4 factorial. And if I were taking the AP exam, I could leave it just like that and be totally fine. But I'm a bit of a perfectionist, so I'm going to clean this up a little bit. I don't have to worry about College Board taking off points for me because this is just for educational purposes. It's just good math, all right? And that'll clean up pretty nicely there, okay? All right, now let's move on to part B. So the part B, and I feel a bit vindicated here with a Lagrange error-bound question, and it looks a little complicated, but it really isn't that bad, especially because they're giving us some key information here. So the fourth degree Taylor polynomial for f about x equals 0 is being used now to approximate f of 0.1. And given that the absolute value of the fifth order derivative is got to be less than or equal to 15 between the interval where x is between 0 and 0.5, use the Lagrange error bound to show that this approximation is within this value of the actual value or the exact value of 0.1. So again, I'm not going to completely rehash the Lagrange error bound here. I will, again, link to some videos in the description below that might help you if you need more of a study in this. But what they're effectively giving us here is our m value, which for many of us is really just the trickiest part with Lagrange error. So they're telling us, they're telling us exactly what that is. So we're going to say the following. We're going to say, all right, our fourth order or fourth degree Taylor polynomial evaluated at 0, okay, is going to be approximately equal, is going to be approximated, we're using it to approximate f of 0.1, okay? And so we know based on what's given to us within the original problem, right, that f of 0 is actually equal to 2, right? Which we know is actually equal to 2. So f of 0.1, that value has to be less than or equal to our m value, which is given to us. That is the highest value for our fifth order derivative. So I'm going to just write 15 here since it's given to us. It's less than or equal to 15. This is the maximum value that it could be, times where we're evaluating our function, 0.1, right, minus where it's centered. This is our c value, okay, to the fifth power over 5 factorial. So again, if you want to, I wouldn't write this on the AP exam, but if you just want a reminder in the general form, this is m times where we're approximating it, minus c to the n plus 1 over the n plus 1 factorial, okay, where this is the absolute largest value for our fifth order derivative evaluated at c, okay? And so if I clean this up a little bit, I got 15 over, I'm going to write 0.1 as 1 over 10 now, because that's going to be useful kind of to numerically compare. 5, and if I start cleaning this up, this is 5 times 4 times 3 times 2 times 1, and I can see that 15 would be, can be divided out with that 5, 3, and 1. And so if I just numerically rewrite this as 1 over 8 times 1 over 10 to the fifth power, well, just right away, looking at this, I can see that by multiplying this by 1 over 8, this has to be less than 1 over 10 to the fifth power, right? If I just even clean this up a little bit, I can see that this is 1 over 8 times 10 to the fifth, all of this here. So if my denominator here is larger than the denominator of what I'm comparing it to, this entire value must be less than 1 over 10 to the fifth. So I've just numerically shown what I've got here, and I'm just going to clean this up a little bit. What I've got here is indeed less than 1 over 10 to the fifth. So our Lagrange error bound is showing how good of our approximation our Taylor polynomial is giving us, and it's a pretty darn good one, okay? All right, so let's look at the last part. So for this one now, we're again being told that our function has derivatives of all orders of all real numbers. And again, they're restating all the conditions. Part C, let g be some function where g of 0 is equal to 4 and g prime of x is equal to e to the x times f of x. Okay, so we got to do a little bit here. So we're going to say g prime of 0, okay, is equal to e to the x times f of x. And so since we're evaluating about x is equal to 0, we're going to plug in 0 for our x's. So that's going to be e to the 0 times f evaluated at 0. E to the 0 is just 1. F of 0 is equal to 2. So this is just equal to 2. So now we've got f double prime of x is equal to e to the x f of x plus e to the x times f prime of x, okay? And again, just the product rule. Don't let that kind of scare you off. It's just the product rule. So now we're going to evaluate all of this at 0. So we've got e to the 0 times f of 0 plus e to the 0 times f prime of 0. And taking our given information, right, when we know f of 0 is equal to 2, e to the 0 again is always 1, f prime of 0 is equal to 3. So all of that is equal to 5. So we've got the information we now need. This is g double prime evaluated at 0. I should be clear in my work. Okay, so we're ready to write our second degree Taylor polynomial for g of x. We can say that g of x is approximately equal to some second Taylor polynomial. I can just write something like this, which is equal to the following. Our constant, which was 4, that was given to us here. Our first derivative, let me rewrite that. Our first derivative evaluated at 0, which we said was 2. So we got 2 times x. And then all of our previous work gave us our second derivative evaluated at 0, which is 5, x squared over 2. So this is arguably one of the easier parts, actually, to this problem, since we only needed to find a second degree Taylor polynomial. All right. So again, I'll link my videos to Taylor series as well as Lagrange error if that'll help you better understand this. But if you're pretty comfortable with those topics, then this is a problem pretty similar to what you've seen before. That was the 6th and final question of the AP Calculus BC exam 2023. So if you completed the exam, congratulations. Go celebrate.